Just seen how sets and operations on sets can be used in probabilities. So what we're going to do now is consider how Venn diagrams can also be used for counting and be quite a visual and helpful tool in that particular way. So remember that for the Venn diagram, we will start with a rectangle that represents the universal set and then include several regions. Now, depending on how many regions you have and you want to put them in the most general formation, for 2, we make sure we produce an intersection. For 3, we make sure we produce intersection of any 2 sets and the intersection of all 3. Now, let's take a look, for example, at this first diagram and think about how many regions have we created by plotting these 2 sets inside the universal set. Well, I have this region out here. Let me call it, for example, region number 1. That belongs only to this set on the left, but not to the one on the right. I have this region number 2, that is the intersection of the 2 sets. I have this region number 3, that includes only the right set and not the left one. And I have a region number 4 that lies outside my both chosen sets. So 2-set Venn diagram creates 4 different regions. Think about regions as actually just encapsulated within the closest boundaries that are drawn. So I'm no longer thinking about the full set here. I'm thinking of every single boundary that has been created. So region number 1 is this sort of moon-like region. Region number 2 is bounded by these little fences and is here, and so on. If I have 3 different sets, I will have more regions. So I can start labeling them. It doesn't really matter how you label them. We're just counting the regions here just so I can point out the fact that the number of regions is different than the number of sets. So for example, I can say this is one region, this is another region, this is yet another one, and so on. So all together, if I go around the entire picture, I will see that I have myself 8 different regions. Again, regions in this case are considered to be what is within the closest boundaries. So region number 2, for example, is bounded by these things. So if I were to label the sets, let's say we call them T, S, and R, and let's say I wanted to describe what region number 3 actually is, I can describe it in terms of set operations on T, S, and R. Region number 3 is actually the set S together with the intersection with set R, but outside of set T. So S intersection R, intersection not T. Now, for counting with Venn diagrams, we're going to really be careful about only including information within the region that sits exactly within this region, okay? So the numbers that you're gonna put down are for elements only in that specific region. Let's see with an example what I actually mean. So suppose I have a class with 25 students. So that is my universal set, and I can start drawing the Venn diagram for that. I have a universal set of my class with overall 25 students. I'm not going to put down 25 anywhere yet because I don't know what region that belongs to. 20 students like chocolate chip cookies and 15 like oatmeal raisin cookies. 12 like both types of cookies. So first of all, let me actually define my sets. Let's say set C is going to be students who like chocolate chip cookies, and let me call it maybe R for oatmeal raisin, are going to be students who like oatmeal raisin. Now I know that that means that I have 2 sets to draw within my Venn diagram. So I'm going to go ahead and draw 2 circles here, and I'm going to label them as C and R. Now I'm going to try to put the numbers in that correspond to a variety of information. First of all, let's think about what we cannot do. What I cannot do is put this number 20 anywhere, because this number 20 corresponds to all the students who like chocolate chip cookies, which means that number 20 actually is the number of elements in this set here, but this set is not a region because there's yet another boundary right here. So 20 is somehow distributed between this entire region. Some students fall outside of the smaller boundary and some fall within it. So I can't put 20 in the middle because I don't know exactly how many there are here and how many there are here. Same for 15. 15 is a number of students that like oatmeal raisin, which means that 15 is the total number here, but there's more than one region. 12 is the number of students who like both types of cookies. Both means the intersection, and that means this region right here. There's no more boundaries in the middle of this region, so 12 is the number I can actually place. 12 students are in the intersection. With this information, I can use the other numbers and place them correspondingly. So let's revisit the other numbers again. There are 20 students who like chocolate chip cookies, which means that there are 20 students within this entire circle. 12 of them are here, so how many of them have to go outside if there's 20 in total? Well, I can subtract the 12, and therefore I will be left with 8 students out here. So let's double check it. If I think about the chocolate chip lovers, then I have 8 plus 12, which is 20. For the oatmeal raisin ones, there are 15 students, so there must be 15 overall in this set. 12 of them are here, which means that 3 more have to live out here. Have I used up all of the information altogether yet? Well, I haven't placed this number 25. So there are 25 students in the entire class. So do they all like chocolate chip or oatmeal raisin or whatnot? What can I do with this 25? Let's take a look at what I have so far. So far I have students who like chocolate chip or oatmeal raisin. And I have 8 plus 12 plus 3 of them. So let's note that down. 8 plus 12 plus 3 is 23. I have 25 students altogether, which means that 2 are unaccounted for, which means that they live out here in the universe and not liking either chocolate chip or oatmeal raisin cookies. With this information, I can already start counting all kinds of different things. So for example, this first part asks, how many of the students like at least one type of cookie? At least one means they like chocolate chip or oatmeal raisin, or maybe both. At least means I'm looking for the union, the number of elements in the union of C and R. Again, remember that I can denote the number of elements by n, or I can denote it by simply the vertical bars, whichever one you prefer. And there are, in fact, multiple ways to count using the Venn diagram that we've already created. So how many of the students like at least one type of cookie? Well, I can say that it's everybody except for the kids who don't like either of the cookies. So I can say that this is 25 kids altogether minus the 2 students that do not like either cookie. Or I can say, well, it's everybody in the union, so I'm going to take a look at what regions within here I can include, and it's going to be 8 plus 12 plus 3 altogether. Okay? Or maybe I can count in some different way. It is up to you to discover what works best for you and how you prefer to reason this out. As long as your reasoning is sound, the actual method by which you're calculating does not matter. How many of the students like exactly one type of cookie? So not both, exactly one. It can be either chocolate chip or raisin, but not both. So I can see here that I'm going to have 8 plus 3, or overall 11. This is just one of the ways to actually calculate this as well. So maybe think of some of the other ways that you can approach this calculation for both of these parts. Let's take a look at the next example. This one is going to be a little bit bigger, and so we're going to have more regions to work with. There are 194 countries with flags. There are 145 flags that have red, 132 that have white, 104 that have blue. And then we're going to have more detail. There are, in fact, 103 flags that have both red and white, for example, Canadian flag, 66 that have both red and blue, 73 that have both white and blue, and 52 that have all the 3 colors. So I have myself a universal set with 194 elements. Here's my universal set. And I'm going to have 3 different subsets of it. So I'm going to have R representing the set of countries that have flags with red in them. Flags with red. I'm going to have W that represents the set of flags with white. And I'm going to have B that represents the set of flags with blue. So I'm going to place all of my 3 regions here. I'm going to try to draw them a little bigger because it's nicer to actually see the corresponding regions and not have to cram your teeny tiny little numbers in. So I'm going to have the red ones, the blue one, the white ones, and the blue ones. How you actually label your sets doesn't matter. So for example, if you go through this example and you label red, white, and blue, it doesn't matter whatsoever. Your picture will look different, but the answers to your questions, the final numbers should be exactly the same as mine. Okay, so I know that altogether I have 194. But that's not something that I can place in my Venn diagram yet because I have no idea where 194 goes. I know that it's the total number of all the numbers that I'm going to have to plug in, but I can't put anything from this information yet down. Next up, 145 flags that have red. So once again, that means that this region has 145. But this isn't one singular region. There is subparts within it. So I can't just write down 145 here because that's not what this region has. 145 is distributed amongst all of these regions within R. Some of them are here, some here, and some over here. Total, 145. But if I write 145 here, that means I mean only in this region, discounting everything else that might actually happen. So that's not going to work. I can't place this number in yet. For the same reasons, I can't place 132 and 104. Let's see if narrowing it down helps. 103 flags have both red and white. Both red and white is the intersection between the set R and the set W, and so 103 has to go here. But I'm facing a similar problem. I have no idea how many of them are in this top region or how many of them are in this bottom region, but I certainly have the boundary separating them. So I can't place this number in yet, and same for the other 2 intersection numbers. 52 flags have all 3 of the colors. All 3 of the colors represents this middlemost region here where all 3 sets intersect. And this is one singular region, which means that 52 can be placed directly into it. And now I'm going to work my way back out. So if 52 is here, let's take a look at what we can have. So for example, 73 flags have both white and blue. So 73 flags have white and blue, which means that they're in the intersection of the 2 sets. There's 73 here in total. This region, this like football looking one region, 52 of them here. So how many have to go here for the total of 73? Okay. We can figure that out by simply subtracting. It's going to be 21. And again, we can common sense check it. Are there 73 flags in this intersection now? 52 plus 21? Yes, indeed, there are. And you work your way back out through the intersections first and then through the sets by subtracting the corresponding numbers. I suggest you pause the video here and try to fill the rest of this Venn diagram by yourself before coming back and seeing what numbers I got. Okay, so working back out, I have 66 have both red and blue. So 66 goes here. With 52 in that region, it leaves me with 14 flags in this region here. I have 103 flags that have both red and white, which means 103 flags go in this region here. With 52 there, it leaves me with 51 for this region. And now back to the full set. So I have 145 that have red, which means that 145 has to live within this entire set. 145 minus 51 minus 52 minus 14 is the number that's going to have to go in here. So that leaves me with 28. Okay, I'm not doing this in my head. I've already done my draft work, so you will actually have to write it out. But again, checking for common sense, I can make sure that these numbers all added up together will give me 145. Proceeding in a similar fashion, I will have 8 here and 17 over here. Now, I can see that with 194 countries altogether, what I've accounted for so far, adding up all of these numbers, leaves me with 191 countries, which means that there are 3 countries that have no red, no white, and no blue on their flags. Okay? There you go, true information, although I actually think that one of the flags has changed, so this number is now a little bit wrong. Bonus question, try to find out which countries have no red, white, or blue on their flags and what those countries are. Okay, now that we have all of the regions labeled with the number of elements in them, we can answer all of the questions here. How many flags have at least one of the 3 colors on them? At least one of the 3 colors means I'm not looking for these 3 that don't. I'm looking for everything that lives inside all of these sets. So overall here, I'm going to have 191. How many flags have white, but neither red nor blue? So I'm interested in the countries that have white, but not red and not blue. And that leaves me with 8 countries and their flags out there. How many flags have red but not blue? So I want red but not blue. Doesn't say anything about the white, so I can include that. So it's going to be 28 plus 51. Let me write that out. 28 plus 51. So overall, that would give me 79. And then finally, how many flags have exactly 2 of the 3 colors? Exactly 2 of the 3. So it can be red and blue or white and blue. So for example, red and blue, exactly 2 of the colors. I cannot account for this number because it has exactly 3. But I'm interested in red and blue, so this number, red and white, this number, and blue and white, so this number. So here I'm going to have 14 plus 21 plus 51, which overall will give me 86. Make sure you go through and understand how to label this diagram and then how to use your labels to answer these types of questions. Venn diagrams provide a great visual representation of how to count with sets, but let's think about how to do it using the actual set notation. So here I have a set A, B, and C, and I'm asked to count the number of the various sets and their subsets. So again, N of A is the number of elements in A, which can also be denoted by the vertical bars. So how many elements are there in A? Well, that's pretty straightforward. I can see all of them. There are 3. How many elements are there in the set C? 1, 2, 3, 4. So there's 4 altogether. Now, how about the number of elements in the intersection of the set A and C? So I have to look at what A and C have in common. That will form my intersection. And then I have to count the number of elements in it. I'm going to write it out so that for the first time, so that it's a little bit more obvious. What is the intersection of A and C? What elements do they have in common? Because the sets are so small, I can simply do it by inspection and notice that there's only one element they have in common, and that's element A. So the intersection of the 2 sets is a sort of singleton here, element A, and so the total number of the elements in the intersection is just 1. Now, what about the number of elements in the union? So if I take the union of a set A and the union together with the set C, how many elements am I going to have in total? I know that separately, the sets have 3 and 4 elements, so maybe the answer is just 7, because I am uniting the sets all together. Now, before we jump to conclusions here, let's write out the actual union of the 2 sets. So I'm going to start by listing all the elements in A, C, E, and then listing all the elements in C, A, B, 1, 2. But of course, you remember that in sets, repetitions should be discounted, and I have this element A that in fact occurs in the intersection repeated in both set A and set C. I cannot double count this, so I'm going to strike it out. So altogether, I have 1, 2, 3, 4, 5, 6 elements in their union. So notice how because the common element cannot be counted both times, the answer is not just the sum of the sizes of the two separate sets. Now, how about the number of elements in the intersection of B and C? So here I have, this is my set B and this is my set C. They have nothing in common, so the number of elements in common is going to be 0. What now about the number of the elements in the union of C and B? So notice that the number of elements in B is 4, so let's write that out. So what do I have for my union? I'm going to have all of these elements followed by all of these elements. I can write it out the same way I wrote out here. But in this case, because the intersection is empty, they will have nothing in common. So I won't have to strike anything out as occurring more than once. I will simply list all of these elements, and there will be 8 of them in total. There are no overlaps. So if I were to sketch a little Venn diagram for each of these union calculations here, I might notice some kind of a pattern. So here, for the first set, I have set A and set C. Their intersection contained an element, which means that when I was counting the number of elements in the union, if I went to count the number of elements in A and then the number of elements in C, I would have counted this intersection twice. This element was counted as part of A and as part of C, and therefore had to be striked out. If I had these two sets here, C and B, to begin with, I know that they have no common intersection, so they are actually completely disjoint, which means that if I were to now count the number of elements in their union, I can count everything in B followed by everything in C, and I'm not worried about overlap, and therefore I'm not worried about having to strike out repetitions. This leads us to formulating the so-called principle of inclusion-exclusion, or PI for short, principle of inclusion-exclusion. If I have two sets, A and B, then the number of elements in the union is going to be the number of elements in the first set plus the number of elements in the second set minus the number of elements in their intersection. So let's check to make sure that this matches our intuition from examples above. I'm going to count all the elements in the first set and then all the elements in the second set, and I'm going to have to take out the intersection because I've already accounted for it once before, right? Or on the picture, I can count all the elements in the first set, and that will correspond to the shading here. I can count all the elements in the second set, but now I notice that my intersection has been double shaded, which means that I have to take out one of its occurrences in order not to count an element more than once. Principle of inclusion-exclusion doesn't just work for two sets, it can be generalized for three or more. So for three, what do we have? If I am going to produce a Venn diagram here, it might help with visualizing what is going to happen. So I have three sets, 1, 2, 3. Again, in the most general position, they will all intersect with each other and all three of them together. What's going to happen if I'm going to count the number of elements in the union one set at a time? So let's say I count the number of elements in the set A, and then I count the number of elements in the set B, and then I count the number of elements in the set C. So I've counted the number of elements here, and then the number of elements here, and then the number of elements over here. Every single intersection will have been counted more than once, right? So number of elements in A will count this, and then number of elements of B will count this, which means that everything in the intersection got counted twice in here. And same for the other two intersections. So that means I have to subtract the number of elements occurring in each single intersection. So A and B, A and C, and then B and C. Okay, now let's make sure that what we have now is correct. So what I've done is I've subtracted, so let me label them, for example, A, B, C. I've subtracted the intersection here. I've also subtracted the intersection here. So I've subtracted it twice, which is good because I've overcounted by that. But then I went ahead and subtracted one more time. So this middle piece got subtracted 3 times. It got added 3 times and then subtracted 3 times, which means it's not accounted for at all anymore. So I have to add it back in. So I'm going to add the number of the elements in the intersection overall. Okay? And this is actually how we generalize the principle of inclusion-exclusion to any number of sets. We're going to start by accounting for all the full sets. Then we're going to subtract all of the 2 by 2 intersections. And then we're going to add all 3 set intersections. And then if there's more sets, we're going to subtract all the 4 intersections and then add all the 5 ones, and so on and so forth. We're not going to work with examples that have more than 3 sets, so you can actually just write it out in this shape and be fine with that. Let's see how we can apply the principle of inclusion-exclusion to actual problems. So I have a New Year's Eve party with 50 people in total, 25 people who had sparkling wine, 35 people who had cake, and 15 people who had both. I am wondering how many people had wine or cake or both. So they've actually enjoyed some of the food-like elements. What do we have? So let me just first of all denote my sets. W is going to represent people who had wine. And I'm going to have C represent people who had cake. U is going to be my universal set, so all the people present at the party, all 50 party people. Now, I can draw the Venn diagram the way that I have before and think about what the question is asking and how I can label my regions within this diagram. So wine and cake. So what I have is 25 people had sparkling wine, so 25 people go here. And as we just discussed, I can't quite place it because I don't know which of the 2 regions it belongs to. 35 people had cake, 15 people had both. So I know that 15 is the number in the intersection. Now, let's see what the question is asking and see if we can answer it by applying the principle of inclusion-exclusion directly without referring or relying heavily on the Venn diagram. How many people had wine or cake or both? So or represents union. So what I'm interested in is the number of people in the union of the wine and the cake. As per the principle of inclusion-exclusion, in order to count the union, I can count 2 sets separately and then subtract out the intersection that has been counted both times. So the number of people who had wine plus the number of people who had cake minus the number of people who had wine and cake. Because once again, this number will have been counted both times, and therefore I have to subtract 1 occurrence of it. Now, this is quite convenient, really, because I actually already have all of these numbers right in the text of the problem without even ever having to draw the Venn diagram. The number of people who had wine is 25. The number of people who had cake is 35. And the number of people who had both is 15. So putting that all together, I'm going to have 45 people who had wine or cake or both. If you would like to double check that with the Venn diagram, we can go through and fill in the rest of the numbers now, just to support our justification in a different way. So I have 15 people that had both, 25 people had sparkling wine, which means 25 people has to go in that entire circle, which leaves me with 10 people out here. I have 35 people that had cake, so 35 has to go in this entire circle, which leaves me with 20 people out here. And now, the number of people who had wine or cake or both corresponds to the union of the 2 sets, 10 plus 15 plus 20. So 10 plus 15 plus 20 will give me the same 45, but in a different kind of way, right? So again, to support the principle of inclusion-exclusion visually, I'm counting the number of people who had wine, which is 25, the number of people who had cake, which is 35. I notice that the intersection has been counted twice, so I take out 1 of its occurrences, so I don't count these 15 people more than once. Both of the ways produce the exact same answer. Okay, so this is just giving you another way to approach the same problem. On the previous page, we had the example about the flags, and let's revisit it by using the principle of inclusion-exclusion. The question, the last of the questions there asked, or maybe let's count the first one. How many flags have at least one of the three colors on them? At least one of the three colors corresponds to the union of the three sets. So this means that the flag has red or white or blue, which means that at least one of the colors is present, that one of the colors that was specified is present. Now, applying the principle of inclusion-exclusion, we're going to have to look at our three-set formulation here, which says that I have to add up all these sets separately. So the number of flags with red, the number of flags with white, the number of flags with blue, and then I'm going to have to subtract the intersection of two of them with each other. So minus the number of red and white, minus the number of red and blue, minus the number of, which one am I missing? White and blue. But as we've discussed, I've now, the overall middle intersection, I have accounted for it 3 times here. I have subtracted it 3 times here. So I have to add it back in to ensure that it's in fact present. R intersection W intersection B. If I put all of these numbers all together with the numbers from the previous page for the flags, I'm going to have 145 plus 132 plus 104. Those were all of the numbers that corresponded to flags of having one color each. And then I'm going to have to subtract all of the intersection numbers, 103, 66, and 73. Be mindful, I'm not actually sure that these are listed in the same order, but the order here doesn't matter. And then I have to add in the overall intersection of the flags that have all 3 colors of them, 52. If you carry on with this arithmetic, you will get 191, which is what we got with the Venn diagram on the previous page. So again, confirming our answer using Venn diagrams by using the principle of inclusion-exclusion. Next up, we're going to think about how the principle of inclusion-exclusion applies to probabilities. But before we do that, let's define what it means to be mutually exclusive. We have 2 events, or generally 2 sets, that are called mutually exclusive if their intersection is empty. So E intersection F in this case is going to produce an empty set. We have seen that on the previous page with an example before, that if we do have no overlap, then this might actually somehow simplify our principle of inclusion-exclusion calculations. For probabilities, the actual principle is exactly the same, because remember, we're simply dealing with sets. It's just that these sets now represent sets of desirable or total outcomes. So in order for us to calculate the probability of the union of the 2 sets, that's going to equal to the probability of the union of the one set plus the probability of the other set minus the intersection. Now, if the 2 sets or the 2 events are mutually exclusive, that means that their intersection is empty, which means that the probability or the number of elements in that set is 0. So that is the one case where we can ignore the third term here because simply it's actually 0. There is no overlap, so we don't have to worry about accounting for it. Because probabilities are between 0 and 1, we can actually derive one more very useful rule that is called a complement rule. For an event E, we have that the probability of E happening is 1 minus the probability of E not happening, or the probability of E complement. And that is going to come in handy with calculations as yet another way to actually compute something. So let's take a look at some examples here. Suppose we have 2 events, E and F, such that the probability of the first one is 0.6 and probability of the second one is 0.25. We would like to compute the probability of the union if the 2 sets are mutually exclusive. A good rule of thumb, or a rule just in general to remember, is that because these are probabilities, these will still have to lie between 0 and 1. So if you ever get over 1 for probability of something, you know you should go back and check your work because you've made a mistake somewhere. So what do we have here? We would like to compute the probability of the union, and as per the principle of inclusion-exclusion, we have one case or two cases if you prefer. I have to add the probability of the first event plus the probability of the second event minus the probability of the intersection. Now the sets are told, or the events are told to be mutually exclusive, which means that this is simply a zero. And what do we have in terms of the other two? Probability of E is 0.6, probability of F is 0.25. So we're going to add those numbers together. 0.6 plus 0.25 minus 0, you don't have to write it out, equals 0.85. And that's it. If you prefer, you can draw a Venn diagram here, just a quick sketch. I have two sets that are mutually exclusive. Therefore, the actual number of the outcomes for the probability in the intersection is going to be the number of the elements in one plus the number of the elements in the other. Let's take a look at our next example here. We have a bag with 12 marbles in it. How exciting. The marbles are actually numbered from 1 to 12. The first 6 are yellow, the next 7 to 10 are green, and then 11 and 12 are purple. Suppose we select one marble from the bag. No idea what color it is. What is the probability that the marble is green? So remember, once again, let's say green here, probability that something happens is the number of desirable outcomes divided by the number of total outcomes. That formula will never change. The number of total outcomes is always easy to determine immediately. What is the total number of marbles here? The total number of marbles is 12. The number of desirable outcomes here is the number of green marbles that I can draw. How many marbles are green? What do we have? 7 to 10. So 7, 8, 9, 10. 4 of them are green. And therefore, the probability of drawing a green marble is 4 over 12. Or if you want to simplify, 1/3. What is the probability that the marble has an even number on it? Okay, so once again, we're going to have our desirable over total. Total I already know, it's still all the marbles, so it's going to be 12. But what are my desirable outcomes here? So it's going to be the cardinality of what set? I want an even number, and I am working with the marbles that are numbered from 1 to 12. So 2, 4, 6, 8, 10, and 12. So on top here, overall, I have 1, 2, 3, 4, 5, 6 outcomes divided by 12 total, or 1/2. What is the probability that the marble is green and has an even number on it? Okay, so probability green and even, and of course corresponds to the intersection. So what are my desirable outcomes versus total? So the total outcomes, I still have 12 marbles. What are my desirable outcomes? It has to be green, so it has to be between 7 and 10, and it has to be even. So what are my choices of the numbers between 7 and 10 that are even? Well, there's only 8 and 10, so that's going to be my entire numerator here. The marbles that are both green and even are only 8 and 10, so only 2 of them out of 12. What do I have next? What's the probability that the marble is green or has an even number on it? So or indicates the union. And this is where I can actually, instead of listing all the possibilities, use the principle of inclusion-exclusion. It's going to tell me that the probability of green or even is the probability that the marble is green plus the probability that the marble has an even number on it minus the probability that it's green and even. Now notice that I know that this is going to be a useful thing to calculate here because I already have all the pieces in this formula calculated above. And so I am not going to have to do any extra work, but just combine the numbers. So the probability that the marble is green is given by part A of this question, 4 out of 12, plus the probability that it's even is given by part B of the question, 6 over 12, minus it's green and even, so 2 over 12. In fact, not simplifying my denominators here is actually better because now they all share the same denominator, which is 12. And so I can add across the tops because it already has common denominators. 4 plus 6 minus 2 is going to be 8 over 12. And there we go. You can, of course, calculate this probability directly as well by going through the same formula one more time. Green or even means I have green marbles and then have to go through the rest of them looking for the even ones. And there should be 8 possibilities out of the 12 total options. Okay, let's take a look at this next example. Suppose I have two events, A and B, and I have an experiment knowing that the probability of an event A is 0.4, probability of event B is 0.6, and the probability of the intersection is 0.1. So notice that these are not mutually exclusive events anymore. And I'm asked to calculate the probability of some sets that involve both the complement and the intersection. We can still use the Venn diagrams because probabilities can be thought of as the sets within the universal set of the actual all possible options. So this is my universal set altogether. Whatever I draw in it has to be less than 1 because that's what the probabilities tell me. And I have two sets, right? I have set A and set B. So I'm going to draw the Venn diagram, and the numbers I'm now placing will correspond to probabilities, not the numbers of elements. Okay, so there is an important distinction. Maybe let me write it out. So the numbers on the Venn diagram will now represent the actual probabilities. So no longer the actual physical number of elements in there, but probabilities. But everything else will work the exact the same way, probabilities. So what am I going to have here? I have that the probability of A is 0.4, but again, I can't put that down because I have more than one region within A. Probability of B is 0.6, also can't put that down, don't know where to place it, but I know that the probability of the intersection is 0.1, and that is something I can place. And then I'm going to work my way out. So probability of A is 0.4, which means that overall there's 0.4 in this entire set. 0.1 belongs to this region, which means that I need 0.3 to live out here. And same logic for B will produce 0.5 out here. I can also then calculate what happens to be on the outside altogether, because I know that the universal set of the probability, everything has to add up to 1. So whatever goes out here is going to be 1 minus 0.3 minus 0.1 minus 0.5. And that turns out to be 0.1, and that's what I'm going to place out here, right? I took 1, which is the total of the probabilities, and I've subtracted everything that lies within these two circles, 0.3, 0.1, 0.5. Excellent. Now, what are the probabilities that I'm supposed to account for? There's two of them. Probability not A intersection B and probability A intersection not B. So I just need to decide where those sets are. Not A intersection B. So I'm going to take everything in B and intersect it with everything not in A. Okay, so what is common to B and not A turns out to be this region right here. And I can see that the probability there, because I've already marked my entire diagram, is going to be 0.5. So this really combines your skills of working with Venn diagrams in terms of labeling the regions, and also working with Venn diagrams in terms of thinking of what regions correspond to this kind of formulaic description of it. A intersection not B. So I have A intersection everything that's not in B. So what do I have altogether is, of course, this portion right here. And again, because my diagram is already fully marked, I can simply read the number off, 0.3. Excellent, we're done with this example. Now I'm going to look at one more way to record probabilities and calculate them. We're going to start with the sample space that's denoted S1, S2, all the way through Sn, so n possible outcomes here. And we're going to actually record the probabilities in so-called probability distribution table. Outcome followed by probability. So the outcomes go on top and the probability corresponding to that particular outcome goes on the bottom. So this will list all the possible outcomes will have to go on top row. So not like an event where only a subset of them does, all the possible outcomes have to go there. And on the bottom, we have all of their respective probabilities. So you do have to align the probability to the actual outcome. One thing to notice here is because we do have all the possible outcomes and listing their probabilities, we will have that P1 plus P2 plus all the way up to Pn will have to add up to 1 because we are listing every possible outcome. Just to see how it works within a simple example, let's construct the probability distribution table, something has to look like this, for the experiment of rolling one die and recording the result. So, first thing we do in this probability table is we have to start with the outcome and its probability. What are the possible outcomes for the experiment of rolling one die? If I roll one die, what are the possible results that I'm going to see? Well, I either roll a 1, a 2, a 3, 4, 5, or a 6. These are all of my possible outcomes. And now all I have to do is write down the probability of each one of them occurring. So what is the probability of rolling a 1? The probabilities are calculated the same way as we always have been. The number of desirable outcomes divided by the number of total. So if I roll a 1, what's the probability of that? The desirable outcome, there's only one way to roll a 1, and the total outcome is there are 6 possible ways to actually roll a die. So the probability of rolling a 1 is 1/6. What about the probability of rolling a 2? Well, the number of total outcomes is still 6, and the number of desirable outcomes is just that one option when I roll a 6. So it's still 1 out of 6. What's the probability of rolling a 3? 1 out of 6. 1 out of 6 for all of them if the die is in fact not loaded. And so what I notice here, again, just as a secondary check, is that if I add all of these together, 1/6 added to itself 6 times, I will get a 1. So I have covered all the possible options. What we have is now the ability to use this table to not just write out all the outcomes and all probabilities, but calculate something about a specific event. So if I have that the event being a subset of all the possible outcomes is S1 through Sk, not Sn, then the probability of that will be the sum of the probabilities of the possible events all the way up to Sk. Okay? And I know that this is a bit of a handful in terms of notation, so let's do an example. Suppose the event E is the event that we roll an even number when we roll a die. How are we going to compute the probability? We can, of course, do the desirable over the total as we always have, but let's try to use the probability table. So first of all, our event E now corresponds to the event of rolling a 2, a 4, or a 6, because those are all the even numbers. Using this table, I can see that my 2, let me highlight them here maybe, my 2, my 4, and my 6 are of course in the outcomes because I've listed all of them, but I've also already computed their actual probabilities. So now, instead of computing everything from scratch, I can simply say that the probability of the event is the probability of rolling a 2 plus the probability of rolling a 4 plus a probability of rolling a 6. Notice that I cannot roll, like there's no intersection between any of them, so that's why I can simply add them all together. They're in fact mutually exclusive here. The probabilities of each one of them separately have already been listed in the table, so I can simply add them up. 1/6 plus 1/6 plus 1/6, which will result in 3/6. Which of course, if you were computing the number of total over the number of desirable over the number of total, you would see that the number of desirable is 3 and the number of total is, as always has been, 6, producing the exact same outcome. The tables, though, are very useful for things that are not very easy to see immediately. So more complicated data structures and data sort of recordings. So let's see what we can do with this example here. After the most recent set of sunny days, there have been 75 motorists involved in automobile accidents, and they were surveyed about whether or not the accident was their fault and what type of tires they actually had on their car. Here is the summary of the findings. So notice that I have two rows here, one corresponding to motorists that said that they were not at fault, and one corresponding to the motorists said that they were at fault. And I have three different columns that corresponds to three different types of tires: the winter tires, all-season tires, and summer tires. So how do we read this table? The number here, so number 8, for example, corresponds to the row and the column that it resides in. So that means 8 motorists were at fault and had winter tires on. This means that there are 12 motorists that were not at fault and that had all-season tires on. So the one column that we can add is going to represent the total per row, and one row we can add is also going to represent the total per column. So this total here will actually total up all the numbers in the row. So the total number of motorists not at fault is 8 plus 22 plus 20, which will end up being 50. This number here will represent all the motorists that were not at fault, independent of what tires they had. So 3 plus 12 plus 10 altogether is going to be 25. And then we can add down the columns as well. So the total number of motorists on winter tires is 8 plus 3. Again, not accounting for what tires they had. We don't care about the tires. We don't care about whether they're at fault or not. We only care about the tires. In this column, we only care about motorists with all-season tires. 22 plus 12 is going to be 34. And finally, last column, summer tires, is going to be 30 in total. Note that if I add down the total column, I'm going to get 75. And if I add down the total row, I'm also going to get 75. And 75 is how many motorists in total were actually surveyed. Excellent. Now that we have this table, we can go through and calculate various probabilities using it. What is the probability that the selected motorist was at fault and had summer tires on their car? The probability that they were at fault, let's write that down, and had summer tires. Now, where are we going to get this information from the table? Well, I can see that at fault and summer tires will reside in this cell right here. Now, of course, that's just the number of motorists, and I would like to know the probability. So we are going to go back to our handy-dandy number of desired outcomes divided by the number of total outcomes. Desired, meaning I am interested in those motorists that were at fault and had summer tires on, which there are 20 of, and the number of total motorists that were surveyed was 75. So 20 out of 75, which is about 27%. What is the probability that the selected motorist was at fault for the accident? No mention of any kinds of tires here. So I am just interested in what is the probability that if I choose a random person from the set, they're going to be at fault. Again, I am using my trusty formula, number of desired over number of total. The number of total, of course, doesn't change. It's still going to be 75. But now I'm interested in what is the total number of people at fault. Well, independent of the tires, that means that I'm after all the numbers in this row, which I've in fact already totaled up to be 50. So 50 out of the 75 is the probability that a randomly chosen person in this survey was at fault. So about 67%. Notice that, maybe I should write this down, if you actually calculate that, you will get 66667 or something like that, which corresponds to the 66 or 67, depending on how you round, probability, 67%. Let's take a look at this last one here. Given that the selected motorist was at fault, what is the probability they had summer tires on their car? So again, we're going to look at our number of desired divided by the number of total. And in this case, it's going to be a little different. And this is going to be sort of the most complicated case, because you got to be a little bit careful. Given that the selected motorist was at fault, so my total isn't everybody anymore. My total is the number of motorists that were at fault. I'm given this additional information, so I'm actually going to restrict the total. I know that this person was at fault, so the number of total people I'm looking at are just the ones that were at fault, which I know altogether there are 50 of. So my total isn't just all the motorists, I'm reducing my total to only the ones that were at fault. Given that, what is the probability they had summer tires on their car? So I'm looking at just this row of my table. They are at fault, which means that there's 50 total, because again, I'm zooming in on just this row. I'm interested in the probability they had summer tires on. So my desirable outcome are summer tires. And there I have 20 of them. So 20 over 50, which is about 40%, right? So careful in reading. If you have something that has been given to you as additional information, you might have to adjust your total, which will then, of course, give you a different number. Another way of thinking about this is, given that it's at fault, reduces this entire table to just one row, not two rows. So looking at this row, the total is the number of total motorists in this row, and the ones with summer tires corresponds to only one of the entries. And that is how we get our answer here.